section with another thing for looking at simultaneous equations. Yeah. So suppose your simultaneous equations can be written as AV equal to B. Okay, like this below. Then it turns out that there's a kind of a formula for the solutions in terms of determinants. So for example, there's one there with y. So now just to show what I'm looking at, so y is one of the unknowns, and that's that. And it's given as a ratio of two determinants, so one determinant divided by another. Now the bottom determinant is just the determinant of A, the determinant of the coefficient matrix. This bottom bit is the determinant of A. And what's going on with the yoke above is that it's taking the constants and it's throwing it in there like that into the y column. Now you might say, how is that the y column? Now maybe we'll see that a bit better in the examples, but this is definitely the y column. Okay, and this, well, if we wanted to call it something, this could be a y. I think we're actually going to call it dy, and we're going to call this thing d. Okay, so yeah, so this is how we're going to do this. So this, it seems a weird kind of a thing. I won't actually prove it. I'm not really exactly sure how it works, although I do know that it does work. Yeah, it'd be very hard to ask you. I'm not sure why it works, but it does work anyway. Okay, so now what I will say is, and I presume I say it at length here, so it's actually, it seems like, oh, that's great, that's an easy way to find solve simultaneous equations. There's only really two good situations. There's only two situations where it's much good. Decimals. So if you've got a simultaneous equation, 2 by 2 simultaneous equation, and numbers are really, really nasty, like with decimals, this Cramer's rule is good. And it's also good if you're interested in not all of the variables, but only one. So rather than, if you don't want to solve x, y, and z, if you just want to find y, this is kind of a good way of doing things. Now, a thing about it is, if you go into a 4 by 4, 5 by 5, 6 by 6, this is just, it's useless because it just takes too long. So we'll just focus on 2 by 2 and 3 by 3. Now there's an example here where it's 2 by 2. You wouldn't use Cramer's rule on this. If I was giving you a 2 by 2 example, I'd probably do it with decimals. And if you try and do a 2 by 2 with nasty decimals, the way that you've seen before versus this, you'd see why this is good for that. Okay, so let's show how this works. So first of all, let's write this as a linear system. So this is the same thing as the matrix of coefficients is 4x, 5y, 1x minus 1y. No significance, by the way, to square brackets versus round brackets. Okay, so D here is the determinant of this. Just right down diagonals minus left down diagonals. And well, let's see about the dx in a moment. So this is equal to, so we'll do the d, so that's the determinant of 4, 5, 1 minus 1. And then the thing on top. So it's basically the same thing, except in the x column. Now this is where you make sense of the x coefficients. Look at the coefficients of x are 4 and 1. So there's that. And for dx, what you do is you replace the x coefficients with the constants. So what you have in here is, instead of the 4 and the 1, the 8 and the 11. So that's what's going on here. So, and then it's easy from here. It's right down diagonal minus left down diagonal. 8 by minus 1 is minus 8. Minus 5 by 11 is 55. And then down here we have 4 by minus 1, which is minus 4, minus 5 by 1 is minus 5. So get minus 63 on top, minus 9 on bottom, which we'll keep, and that's equal to plus 7. So the determinant of the coefficient matrix pops up again in the next thing, so we'll keep that minus 9. So now we'll do y over dy. So this is, so d is the same, it's the minus 9, so we don't have to change anything there. And what about this dy? So it's the same as above, so the blue thing just above it, 4 and 1, but you replace the y coefficients, the 5 and the minus 1, with the 8 and the 11. And then it's the same crack, right down diagonals minus left down diagonals. So 4 by 11 is 44, minus 8 by 1 is 8, over minus 9, and I get 36 divided by minus 9, which is minus 4. And of course, you can check your answers then. So we'll do that here. 4x plus 5y is 4 by minus 4, or excuse me, 4 by 7 is 28, plus 5 by minus 4 is minus 20. That's equal to 8, and the other one says x minus y, x is 7 minus minus 4, well, that equals to 11, so that one's correct as well. So you wouldn't solve a 2 by 2 system like that, to be honest. You wouldn't even use the matrix inverses, but this is useful if the numbers are nasty, if they're decimals. So hopefully we can see, if I just look ahead, we can show you a realistic example where this would actually be used. This is what I mean, these nasty numbers. This is, like, for you to try and do this, it's a bit nasty. Okay. And now this works with 3 by 3 using exactly the same principle. Okay. So what do we got? We got a Brazilian student here making phone calls within Ireland to the US and to Brazil. The rates per minute for these calls vary for different countries, but the total call duration to each country is known. So we want to clearly define 3 unknowns, write down 3 equations x, y, z to form a linear system, write linear system as a matrix equation. If ax equal to b, write x in terms of a and b, and then using Cramer's rule or another matrix method, find the rate per minute. Now the other matrix method is to find the inverse of the 3 by 3, but we're not doing that. Okay, so the question is, what is the unknown? So I think, to me, this is the tricky bit here. I'm going to pause because I'll need to write down the equations. So what's not known, and maybe it's a bit difficult to see this, is the rates per minute vary. So they're the unknowns. The Ireland rate, the US rate, and the Brazilian rate. We know the total duration of each of the calls in each of the months, but we don't know the rate. So they're the 3 unknowns. So let us write this down. So x is the Irish rate, which is a number because it's per minute. We can put in per minute. And we'll just put it into a bracket, so it'll be the same, understood for the other 2. Y is the USA rate, so the cost of 1 minute of call, and Z is the Brazil rate. Okay, that's part A. Now we get into something, we'll probably do one of the equations here. Yeah, so there's a bit of thinking to do here from my point of view. So what I'll write the first equation up here. So the Irish minutes, so there's 90 minutes, and if the rate is x, x is the cost for 1 minute, so 90 minutes will cost 90x. The USA minutes, each cost y, so if there's 120 of them, it's going to be plus 120y. And similarly, Brazil is going to be 180 times z, and that's going to equal the bill. Now, there's no service charge in this. 252. Okay, now I'm just going to write down those equations on a piece of paper beside me. So if I do the other equations in the same way, I get, well, the one I just had there was 90x plus 120y plus 180z equal to 252. And 70x plus 100y plus 120z equal to 184. I think that's October, and then November. 50x plus 110y plus 150z is equal to 206. And there's an idea here is to divide everything by 10. Divide both sides of every equation by 10 will make things easier. So if you don't, so think about Cramer, we're going to do Cramer's rule where you're multiplying along diagonals. If you're doing 100 by 100 by 100, you're getting numbers of a million. It's going to be better if you have smaller ones. So I said here divide by 10. Maybe if you divide by 100, you'll get nasty decimals. So maybe dividing by 10 is the best idea. So divide both sides of every equation by 10. So you get 9x plus 12y plus 18z is equal to 25.2. Next one is 7x plus 10y plus 12z is equal to 18.4. And the last one is 5x plus 11y plus 15z is equal to 20.6. So that's part A and B done. Write it as a matrix equation. That's the next bit. So here we go. So the matrix coefficients is 9, 12, 18, 7, 10, 12, 5, 11, 15. Vector of unknowns, which is called big X here, which is a bit, it's not great because we've got little x and big X, but it's not as bad as little x and little x vector. So the vector of unknowns is x, y, z equal to the constants 25.2, 18.4, 20.6. So this is AX equal B. What's part question D? Question D is if AX equal to B, which we've done, write X in terms of A and B. So this is just a matrix algebra problem. So I got AX equal to B. You want to get rid of this A. So how do you get rid of that A? Well, you multiply by A inverse, but you have to multiply by A inverse on the left. So that's the wrong yoke. Sorry about the colors. I hope the colors aren't more annoying than they're worth. So that's A inverse there, A inverse there, and we're talking AX equal to A inverse B. And now the A inverse undoes the A, so you get X is equal to A inverse B. Now I haven't showed you, and I won't show you how to find the inverse of a 3 by 3, because I just want you to understand what an inverse does. It's not so actually important that you're able to calculate it. So now what we have to do here, now we have loads of space here, so we'll see what we get. So the next question is find the rate per minute for calls to Brazil. So we're looking for Z. Okay, so Cramer's rule says, not actually, just trying to think, maybe we'll try and find it all here. There's probably space. So Z, Cramer's rule, is dz over d. So the easy bit here, yeah, do we space? Hopefully we space. So the easy bit here is the d. So d is the determinant of A. So take A and find the determinant of it. So that'll be 9, 12, 18, 7, 10, 12, 5, 11, 15. And then what does dz do? So dz is the same thing, 9, 7, 5, 12, 10, 11, but instead of the z coefficients, we have the constants. So instead of the 18, 12, 15, we have the constants 25.2, 18.4, 20.6. So hopefully we've space to calculate all this. So in both cases, what we want to do is write down the first two columns again. So that's 9, 7, 5. It's probably, listen, I'll be quite honest, it makes way more sense to calculate these determinants separately. It's just, it's kind of a pain the way I have it going from page to page looking back, so that's why I'm going to try and do it all in one go. 9, 7, 5, 12, 10, 11. And now let's try right down diagonal minus left down diagonal for both of them. So this is going to be some right down diagonal action, right down diagonal action, and then left down diagonal action. Okay, and full diagonals to length 3. So hopefully this all fits. It's not you understand, you'd be better off calculating these determinants separately rather than all in one go like this. This is a bit stupid. Right, so the right down diagonal, so I get 9 by 10 by 20.6. I'm going to the calculator with that. 9 by 10 by 20.6. I'm getting 1854. Now I'm looking up the top now. 12 by 18.4 by 5. I'm getting 1104. I suppose the only good thing is everything is positive. 25.2 by 7 by 11. I'm getting 1940.4. That's a plus there. Take away the left down diagonals up the top. So the first one I see is 25.2 by 10 by 5. It's 1260. The next one is 9 by 18.4 by 11, which is 1821.6. And then 12 by 7 by 20.6. And I'm seeing 1730.4. So what that is the top thing, right down diagonals minus left down diagonals. Okay, now do the same for the bottom. So the right down diagonals, probably a bit easier here. 9 by 10 by 15 plus 12 plus is here. 12 by 12 by 5. Next one is 18 by 7 by 11. Take away left down diagonals for the bottom. So the first one is 12 by 7 by 15. Next one is 9 by 12 by 11. It's 1180. These are vicious, aren't they? Don't like this at all now myself. Plus 900 now. Let's hopefully there's no mistakes there and we get a nice answer out. Now there's nothing guaranteeing saying that the answer should be nice. We'll just see what we get out. I strongly recommend not doing it in one go, so calculating the determinants separately. This is kind of a stupid way of doing it. Anyway, 1854 plus 1104 plus 1940.4, take away with brackets 1260 plus 1821.6 plus 1730.4 divided by first bracket 1350 plus 720 plus 1386 minus 1260 plus 1188 plus 900. Give me a nice number. Oh, no, this is the right answer. So 0.8. So 0.8, whatever it is, euros per minute, something like that. Okay. So that's Cramer's rule. Now we're going to let you do try one here. And there's kind of instructions on it. So I want you to pause it and do it yourself. and when you're finished you can unpause it, and I'll be going through it a bit quicker this time though. Okay, so I'm back now. If you haven't tried it, pause now, otherwise here we go. So you want to find z, so you do dz over d. So d is quite easy. So d is the determinant of the coefficient matrix. So maybe if we'll just write this as a matrix equation: 1x minus 2y 1z, 3x 2y minus 1z, minus 1x 3y 5z. That's the matrix coefficients, times x, y, z equal to the constants minus 4, 8, 0. Okay, so this here is a, and d is equal to the determinant of a. So I want to find the determinant of a. So 1, 3, minus 1, minus 2, 2, 3, 1, minus 1, 5. So what I'm going to do is, I'm not going to use all the colors now, just do the first two columns again. 1, 3, minus 1, minus 2, 2, 3. And I'm going to do right down diagonals minus left down diagonals. So I get 1 by 2 by 5 is 10. Minus 2 by minus 1 by minus 1 is minus 2. 1 by 3 is 9. Take away. Coming back the other way, the first one, minus 2 by 3 by 5 is minus 30. 1 by minus 1 by 3 is minus 3. And 1 by 2 by minus 1 is minus 2. And I'll tidy this up a little just to make sure I don't get it wrong. So it's 17 minus, and this looks like minus 35. That's 17 minus 35 is 52. That's the first one. Now for the other determinant, and it's because it's dz, I need to replace the z coefficients with the constants, and I'll be doing that on the next page. Okay, so dz is equal to, no, I'm just going to write the determinant, well, I'm not even going to write, I'm just going to write the matrix that I'm looking at, which is 1, 3, minus 1, minus 2, 2, 3, and I replace the z coefficients with the constants minus 4, 8, 0. Okay, now I want to calculate the determinant of this matrix. So off we go. So I think what I'm going to do is, I'm just going to start it again here. So 1, 3, minus 1. Now I've seemed to have made this a little bit small. If you make it small, it gets a little bit harder to deal with. I kind of saved it. Write the first two columns again. And do right down diagonals minus left down diagonals. So I get 1 by 2 by 0 is 0. Minus 2 by 8 by minus 1 is 16. Minus 4 by 3 by 3, I think that'll be minus 36. Good? Yeah. The brain's gone a bit thick today. And then the other way, minus 2 by 3 by 0 is 0. 1 by 8 by 3 is 24. And then minus 4 by 2 by minus 1 is plus 8. So we're talking, this looks like minus 20. Take away, the other one looks like 32. So minus 32, minus 20 minus 32 is minus 52. So we got d was 52 and dz was minus 52. So we have that z is equal to dz divided by d. dz we just calculated was minus 52. D is 52. So we found that z is minus 1. Job done. Okay. Now you can use Cramer's rule to find x and y as well, but obviously it takes ages, and as the system gets bigger, it gets even worse. Now I was going to do a final video, which would be a little summary, but it's just so short. We can go at it. In my opinion, the big thing in this chapter really is to just do practicing the arithmetic, the multiplication and stuff like that. So the stuff from week 4 I think is very important. I'll just quickly go over this stuff. So the first thing is you can multiply two matrices together if the middle numbers match, and what size matrix do you get out is n by m. If the middle numbers do not match, you simply say you say it's undefined. A transpose, you swap the rows and the columns. You want to understand what the inverse does. So there's here, this is probably not what you're so familiar with. It's probably more something like this. So say if you got A, B equal to C, and if you multiply both sides by A inverse on the left, that you understand that the A inverse undoes the multiplication by A. And so A inverse undoes the multiplication by A, so you just get B is A inverse C. So you understand that the inverse undoes the action of the matrix. And the other thing is that the inverse of inverse A, well, it's kind of implied here, is that the inverse of inverse A is actually equal to A. Okay, and then I is a matrix that's like the number 1, so I times A is just equal to A. Kind of relevant as well. There's a formula in the tables in the manual for finding the inverse of a 2 by 2. You can use matrix inverses to solve simultaneous equations. Another matrix equation. Matrix is invertible if and only if the determinant is non-zero. And a matrix is not invertible if the determinant is 0. And Cramer's rule is good for finding one of the unknowns, but you can do more. So that's everything on matrices. Things are going to get harder from next week.